How are you doing, guys? Emil here. Today I'm going to be going through the entire workflow for how to do a DFT+U calculation with spin-orbit coupling. Firstly, I'm going to go over to the Hubbard U correction portion of my... Hopefully I'll be able to fix this. If you noticed, I did change the quick nav here, but it doesn't... Oh, it does work. It works for everything besides Hubbard U, maybe? Okay, it works for just particular ones. That's fine. I'll probably have this fixed by the time this video is uploaded. So firstly, we're going to calculate the Hubbard U correction. So you're going to need the ground state, the NSCF portion, as well as the SCF step. So I already did this beforehand for uranium, rhodium, germanium, and I'm working on the titanium, nickel, silicone type. If you have Pearson's crystal database, again, you just export to CIF. Then you open an Investa, export as a poscar, however you want to do it. You could also just have the CIF run locally. And VASP kit has an option. Okay. VASP kit has an option to just transfer, or I should say, convert the CIF file to poscar, and you can see it right here. But again, I have the poscar already. I have the K points from a previous version. All I'm doing here is I'm using a different set of pseudo potentials. Now let's take a look at our poscar file. So URhGe, RH, and RH. So what's particularly important in this case, obviously this isn't the standard poscar, right? It should be uranium 4 atoms, germanium 4 atoms, rhodium 4 atoms. However, we are separating rhodium into its own atom, and then rhodium setting up 3 again. This is again in accordance with everything here. I guess this may not be clear for your poscar because I did not include it. I sort of just ran this entirely from VASP's websites, the website tutorial. Anyways, I'll make a correction here. But again, you have uranium, germanium, rhodium, and rhodium set twice. So simultaneously, you're going to have to take this into account for your pot card, right? So pot create URhGe, RH, RH. And we're calculating for rhodium here. So let's let's move back a little bit because I forgot I'm gonna have to do this process twice for uranium as well as rhodium. So we'll do that. So I'm just changing the naming convention. And now you can see I have the K points set to 684. The NCAR is a pretty standard NCAR. These are all you need to do. So I set the magnetic moments of uranium here to be ferromagnetic, right? All spin up. 0 for germanium and rhodium. We know this, sigma standard, I smear standard. We're going to leave it as per what was done in the VASP tutorial. L orbit we're going to set to 11. L max mix is 4. However, when you're doing, you could leave it as 4 here. Even if you were doing uranium, you could leave that 4. So However, what's important is that if you're working on F electrons and you put in the DFT+U corrections, so once you actually are done with this portion, anyways, you'll see it. This is gonna have to change to 6. So this is pretty much it. I'm gonna set this to 36 cores. I'm gonna double check my in-car. N-core should be set to 6. I'm gonna ignore K-par, everything else. That's pretty much it now. It's since finished up, but we had an N-bands problem. Sometimes this comes up, sometimes it doesn't, and because this is a problem that I want to address now, rather than later on, so I want to make sure I could rely on my actual results here. So if you want to look up how to calculate for your N-bands, this is going to be a metallic system. Some transition metals with open F shells. Obviously, we're working with uranium. We're working with rhodium. We have open F shells with the uranium. So it's going to be N electrons over 2 plus 2 times N ions. So N ions is 12 times 2, 24, 108, 54 plus 24, 78. Yeah, so 78 bands we're looking at, but I like to add a couple more. I'll probably do 90, something like that, and I'll rerun the calculation. Oh wow. Hopefully we won't have this problem later on. And we'll let it run once again. So the next step here is, once we have our, everything's calculated for our ground state, we have to set up, what are we setting up? Self-consistent field, right? Ground state done. Non-self-consistent, NSCF. So I have a script that pretty much does this. Again, I go over this in depth later on. So I'm going to make a lot of subdirectories. Okay, here's what this is going to look like for our 0.15. Okay. This is the only portion that gets changed, the in-car. So previously, all I had were this. Okay, this is where the DFT+U portion comes in. Okay, so LDAU type 3 tells you, okay, you're doing this exact process. We're dealing with RH, the one that turns into the 1, right? This is 3. So again, the third position, we're dealing with SPD 1, 2. The D orbital's there, and again, this changes to 0.15, this changes to 0.15. You're adding this I charge component, and again, everything is fully laid out here. You copy over the poscar, potcar, in-car, K points, wave car, charge car. The in-car has the I charge this, and depending on your system, depending on your system, what exactly you're dealing with here, applying to the D orbitals. Of just the first atom, just the 1 RH, the 1 rhodium. So again, boom, boom, boom. And what I changed in the in-car initially, if you're dealing with an F electron, so when I do this for uranium, I'm going to change the Lmax mix 4 to 6 in the actual non-self-consistent field portion. So again, if you want to look at my particular script, I just had ChatGPT make this. It has a loop, right? For each one, different UJ components, makes different directories, copies all of these over, and it appends by doing the following. So this is not going to be applicable to uranium, because if I'm doing uranium in this exact position, I will have to change these to go over to this position, to this position, to this position. This will end up being 3, and again, Lmax mix will be 6. So what I do, rather than adding a whole line for the Lmax mix to be changed from 4 to 6, is I just change it at the end. But yet again, you'll see, how your particular process turns out. So now that I have all of these subdirectories, all I have to do is, I will have to change job. So I'll just change this to 9. Wave functions are done. Good. And we don't have the error. So that's perfect. Again, you have to be on the lookout for what you do, because I guess I rewrote the NCAR, but I put in the N bands again, and that should be all right. Am I missing anything else? So I'll wait for these few to finish. Okay. So I'm gonna look at so this is how this works. Again, you could use ChatGPT like I did. What this does, it'll go through column 9, and yeah, it will go through column 9. I'll show you exactly how this works. I'll go over to 0.15. Go to the end of the outcar, and we're looking for the total charge. Magnetization? No, total charge. So it should be applying the correction here to the first atom. So it's 1. Oh, hold on. .489. Okay. So we should be looking at atom 9. Atom 9, 7.583. Okay, because it's getting the D of atom 9. That's correct. So 7.583. We look over, this is 7.583, so that's good. Perfect. So, I know this is correct. And go. So next up is the NSCF step. Let me get my charger. Okay. So for the SCF step, you remove iCharge 11 from the NCAR. You copy all these over. This time, you're not copying over the charge car. Again, I have another script for this. Okay. Good. Okay. Right. So now I'll just do that. And now when we go over to something like this, you should see the SCF. So NSCF, SCF. Now I'm going to look over the in-car. Everything's the same, and you don't have iCharge here. So, same exact format. Nice batch job. This is going to take quite a bit as well, like considerably longer than before. So I will do the same process. So we have about 71% CPU usage. That's fine. And you can see a much slower conversions. So I'll check back up on this in a little bit. Our calculations are all done. I'm going to go back to my ground state directory. I'm going to copy out, actually, excuse me. I'm going to get all the D values here. Let me adjust this. It says total F charge. And really, that's not accurate. D or that's more accurate. And then just gotta do that. There you go. So now you want to plot these. You want to see what the correction is going to be. And again, I have a notebook that I used. Do I have this open already? I do. Whatever, that's fine. Get this done just like this, and you can see that, you know, we go in from minus 0.015. Let's pull this back up again. The N minus 0.015 is going to be 7.353. You can see already there's been quite a bit of a difference from the regular, excuse me, this regular super potential to the other ones I did from before. And I believe I did RH_D and GE_ something else. It just gets in your fits. And there you go. So now it's telling us we should have a correction value for the the rhodium d orbital of roughly 3.13 electron volts. So that's it for rhodium, the d orbital. The next video, I'll be doing uranium for the f orbital. So thanks for watching. Please follow along. Any questions, feel free to leave them under this video here.